Condensed matter people. Oh, I'm on YouTube? Okay, I should be careful. So I assume this is recorded, right?
Yeah, if that's all right with you.
Yeah, of course.
Yeah,
As
we'll
long
wait.
as I get the link.
Well, it'll be on YouTube, so yeah, we'll give you the link.
Okay.
So we'll wait a couple more minutes for people to show up.
I think maybe we can start. I'll start recording and then write.
Great. All right, seems good. Welcome to the CMSA Quantum Matter Seminar. Today we have Theo Johnson-Freyd from Dalhousie University and Perimeter Institute to tell us about minimal non-degenerate extensions and anomaly indicator. So thank you very much, Theo.
Thank you to Ryan and Jivan for the invitation. So I want to tell you about kind of very exciting theorem that's new that David Reutter and I proved just let's see, I guess 11 days ago now. A few weeks. This was it's posted on the May 31st because I don't know, we had a deadline. And also these handwritten slides you can download and sort of read on your own if you want. Although I think I was looking through them and the handwriting slowly gets worse as the slides go on. So, and please interrupt with questions. I think this is supposed to be a sort of long seminar with lots of discussions. So feel free to take advantage of that. It's more fun to be able to see and hear people during lectures. Right, so let me dive in and tell you about the results. So I'm going to start. So what we did in the paper with David was to kind of complete the what was a kind of 20-year program in fusion category theory to understand minimal non-degenerate extensions. And I really want to emphasize this was really kind of, there's a humongous amount of work that we were drawing on to do this. It's not like we did it all by ourselves, but I think we've really kind of now understood the whole problem. So let me just sort of start by explaining even the statement of the problem, and I'll try to sort of mix a math and physics language. So I think most people here do know what a braided fusion category is, but let me remind what it is. I'm not going to try to give the precise definition because it wouldn't be valuable. If you haven't seen the definition of fusion category, you should kind of nod along, but it wouldn't help me to say, oh, it's a Caribe complete category with blah, 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 with F and R symbols. That would, that's important, but that would take too long. What it is kind of what it means to be a braided fusion category is that it's a theory of topological anyons in 2+1D systems. So namely, it's the data of the anyons and the fusion and braiding data. And when I talk about braided fusion categories, I do allow some transparent anyons. By definition, so I'm going to use this. By definition, an anion is called transparent if it has this, if it can unbraid with any other anion. And so if you look at the collection of all of your braided fusion category, there's some subcategory of transparent anions. I'm going to use kind of curly E for that subcategory always. So B for braided and E for commutative ring, because that seems to be the letter that, this is actually, I think, Serge Lang's fault, that mathematics, or maybe, I don't know, the French school's fault, because anyway, Serge Lang in his book on algebra uses the letter E for commutative rings. And as far as I can tell, that's somehow where this type of thing comes from. Anyway, this is a subcategory of transparent anions, and it goes under a name. In mathematics, it's called the Muger center of B. And a special case is when this is just vector spaces, meaning that the only transparent anion is the vacuum particle, the sort of manifestly invisible particle, and like direct sumses. And in that case, the category is called non-degenerate. And I should say, like, to actually make this physics, I should add words like unitary. I should work over the complex numbers. Our work with David is actually totally algebraic. We're always over just some arbitrary characteristic zero algebraically closed field. But if you'd like to work with unitary complex numbers things, you won't lose any intuition. So if you actually took a 2+1D topological phase, for any reasonable definition of what a 2+1D topological phase is, and ask what are all of the anyons in that phase, you'll always get a non-degenerate braided fusion category. And conversely, up to these issues about saying words like unitary or not, and that's a sort of matter of taste, any non-degenerate braided fusion category can sort of arises for a unique topological phase. I mean, the second part is sort of depends on what definition of topological phase you want. The first part is definitely true. No matter what definition of topological phase you have, it's going to have the property that if it exists in 2+1D on itself, it's going to have the property that its braided fusion category of particle excitations is non-degenerate. So there's a very natural question. That's a question that you could ask in both math and physics. Let's say I give you some arbitrary, like I go and build some braided fusion category, possibly degenerate. Can you represent it? Can you realize it fully faithfully among the anyons among a non-degenerate category, among the anyons for an actual phase? So can you engineer a phase that has this collection of anyons among them? And the answer is yes, and it's not very hard to do this. And this was known, 20 years ago. So the answer is you write down the Drinfeld double of the category. This is a version of the, a kind of category, or the Drinfeld center. Those words mean the same thing, and it's a version of the doubled Hopf algebra of a group. And then this is completely like a functorial thing, and then Walker-Wang construction, if you like, or Turaya-Viro construction, whatever you want to call it, gives a completely explicit 2+1D phase whose anyons are this Drinfeld center. That topological phase doesn't use the braiding on B, but the braiding on B gives you a way to realize B among the anyons in this Drinfeld center, in this doubled model. And it's as good as a topological field theory can be. It's given by a state sum model. It's given by a commuting projector Hamiltonian model. It's like the best of all worlds. It's also not very satisfying for this question. It's not very satisfying because it was too easy, but we can try to kind of quantify its lack of satisfactoriness. So one of the ways that it's not satisfactory is that if you look at this full collection of anyons, there's a lot of them, and many of them are transparent to all of B. There's sort of too much. What I'd like to do is just add a small number of extra anyons that make up, that sort of can see the Muger center of B. So the definition that Muger proposed back in 2003 was that he said, let's say that a non-degenerate extension, meaning a fully faithful embedding into a non-degenerate category, let's call it minimal if the only transparent to B anyons in the whole thing are the obvious ones at the Muger center. And Muger asked, I don't think it's fair to say he conjectured, I think he asked, does every braided diffusion category have a minimal extension, a minimal non-degenerate extension? Drinfeld gave an explicit counterexample. This is always attributed to unpublished note of Drinfeld's, and I can't find a reference that actually gives a date. It was early on, it was just within a few years, but if anybody in the audience can tell me like when Drinfeld did that, I would appreciate it. Anyway, it was within a year or two of Muger's questions. So. And then there's been a humongous amount of work, including by people in this audience, on this question. Giving, kind of classifying and counting how many extensions exist and when.
Excuse me, I have a question here.
Yes.
When you take a trivial center, do you go to one higher dimension?
No, sorry. So what I meant here is that I take, when I wrote this, what I meant is take B, temporarily forget that it was braided. Just think of it as a fusion category. Take its just ordinary Drinfeld center as a fusion category. That gives you a 2+1D phase. So in a moment, in fact, like on the next slide, I will go to 3+1D.
Okay, yeah, thank you.
Okay. But yes, so this is a great chance to ask. I mean, it's always a good chance to ask questions, but thank you. So as Xiaogang anticipated, to actually answer, to really understand this problem, we should go to 3+1D. So let me explain what the right way to think about this problem. So any braided fusion category has a favorite 3+1D field theory that it selects. In fact, it selects more. It selects a 3+1D bulk theory and a 2+1D boundary condition for that theory. And this is called either kind of Crane-Yetter or Walker-Wang model for B. And I don't know, I think the difference is that Crane and Yetter wrote a state sum description and Walker-Wang wrote a commuting projector Hamiltonian description, as far as I can tell.
Theo, can I ask you a question?
Yeah.
It's about the last slide. Can you say more about this counterexample?
So you can read an explicit description. There's a wonderful paper by that I'll come back to a couple times. So let me just sort of give the reference. So there's a wonderful paper by Galindo and Ramirez, and Venegas Ramirez. Which kind of almost gives already the complete answer to this minimal extension problem. It does everything except for the part that David and I did. And they actually described Drinfeld's specific example, and they seem to kind of either gotten in touch with him or anyway talked to people who had seen Drinfeld's example. So Drinfeld's example, I'll tell you how to construct it. And in fact, like if you want to talk afterwards, I can just give you a sort of universal recipe for counterexamples. Drinfeld's example is the smallest one possible in a particular sense. So in their example, the Muger center is the representation of the Klein foregroup. It's a Tanakian, just representations of a group. It's sort of a nice bosonic object. And there's a kind of cohomology calculation that I'll sort of sketch in a moment, which shows you that it's certainly plausible, certainly allowed, and in fact does occur that you can find Klein 4 group as the Muger center for which there's no minimal non-degenerate extension, and that's the small, that you can't do any better than that. But the Klein 4 group is really, really small. So maybe I'll come back to that question. And if I don't come back to it within like 3 slides, just ask me. But I want to kind of tell you how to actually build it, or I want to at least tell you how to see that it's a counterexample, what the technique is. So it's not the way they did it, but it's the right way to do it. The right way to do it is to look at this 4D Crane-Yetter model that you build from B. This is a nice explicit thing. The boundary observables, this is a bulk boundary system. And if you have a bulk boundary system, it has some boundary anyons, some anyons that are confined to the boundary or possibly confined. Those are precisely B. And you engineer this so that that's true. And you engineer the bulk, well, it's sort of the only thing it can be. And you engineer the bulk to be, yes, so Meng Cheng has answered in the comments the question. You engineer the bulk to be the bulk that it has to be to have this boundary condition. And I mean, this uniquely characterizes the field theory. It's the bulk boundary system with these boundary observables. And then if you compute what are the bulk observables, they're the following. So the bulk line operators, the bulk, you could think of the bulk kind of particles in the bulk are the Muger center of B. This is 4 total, 3 plus 1D. So the particles are just, there's no anionic statistics. They're either bosons or fermions, and they're this Muger center. There are also bulk string excitations. Oh, let me give some notation. So the boundary, even in 2 plus 1D, there's like, I said the bulk observables are B. What I really should have said is that, so the boundary observables, what I should have said is the boundary anyons, the anyons confined to the boundary are the braided fusion category B. Now, in 2 plus 1D, there are also string-like excitations, quasi-string excitations that you can produce. In this one, all of the quasi-string excitations are built from condensing anyons. This is not true generally, but it's true for this boundary condition. So I think they did, like, I tend to use the word Cheshire for a string that you can, this is a sort of word I picked up from Elson Nymark paper. So they're kind of strings that can evaporate. They're strings that look like the Cheshire Cat smile. But they do exist, and it's useful to sort of think about the 2 category of all string excitations in the boundary. And I'm going to write sigma B for that 2 category. It's the same data as B. This sigma just reminds you that it's a 2 category now. And it's a fusion 2 category. And a lot of what allowed us to do this proof was kind of that we now finally have a robust definition of fusion 2 category. Anyway, so in the bulk, there are also string excitations, and they're not all Cheshire, and that's important. So that what that tells you is that there's a priori, and in fact is, more data in the bulk than just its particles content. I can tell you precisely what the 2 category of strings in the bulk is. It's the 2 categorical Drinfeld center of this 2 category. So yeah, and that just sort of follows from this analysis.
The Cheshire strings are the strings that can end?
Cheshire strings are the strings that can end, yes. Because then they sort of, that ending gives a way for them to kind of evaporate into the mix. Okay. I mean, they're the strings that can end, yeah, I mean, this is a topological phase. So the Cheshire strings are the strings that can end in a topological way, but there's nothing else. So it's useful to sort of, rather than working with all of the strings, it's useful to work with equivalence classes of strings modulo kind of being able to condense from one string to another. You take a string world sheet, you take a string might have, that string world sheet might have some confined particles on it.
Excuse me.
Yeah, and you can condense those, yes.
Naive question. Just want to make sure
Yes.
I followed it. I think I certainly heard this terminology about this tensor string or tensor charge. But can you remind me an example, maybe from a group homology theory like Daigle-Witten?
Sure. Let's just take digraph-Witten theory in some large dimension for the group Z2 with trivial digraph-Witten action. There's one non-trivial particle, which is the charged particle, the sort of the Wilson operator for the non-trivial representation is Z2. If you take the sum of, so that's some boson, and you can build a string where that boson condenses. More precisely, what you do is you take the vacuum plus that charged particle, that's an algebra anion. And you can build a string where that algebra anion condenses. What you do very explicitly is your string microscopically is built as like, if you look really, really closely under a microscope at your string, it actually looks like a bunch of particles kind of moving, kind of condensing and producing and condensing. So it looks like some kind of, in space-time, it looks like some network of particles like that.
The way you describe sounds more like a P string. People talk about the particle string, but I saw that there are people use tensor charge or tensor string in the context maybe Presky or around that time people study discrete gauge theory. Are these two contexts the same? Because you describe P string.
I might be misusing the term. I don't know the literature that you're referencing. For me, the Cheshire strings are just any string that can end. And then like I can tell you a full list of those.
Can end by its own, or can end on boundary, or can have an open ends?
Sorry, can just sort of end in the bulk. So the string, you could have a sort of a bit of string that could just like, like an actual, I maybe even have a bit of string lying on my desk, and it would just be something that can end just without having to go to the boundary or anything. You can just sort of, so it's a string that has an interface to the vacuum.
Okay, but let me ask maybe Dominic if he is here, because he also used that terminology for tensor charge.
Oh.
Is that the same context as what you have, Dominic? Or I don't know where Dominic is. Dominic
here?
They should be here.
Well, I got the term from a paper of his, and the example they gave I thought matched the way I was using it, but maybe I misunderstood how they were using it.
Okay, maybe I'll check, compare again. Thanks.
Well, then, thanks. So as I said, like I might be misusing it, but what I meant was that the strings that can end in the bulk, and more generally, you can take there's an equivalence relation where you just say two strings are equivalent if they have a non-trivial interface between them. Two simple strings are equivalent if there's a non-zero interface between them. That gives you an equivalence relation on strings. And one of our first theorems with David was to completely count those equivalence classes. And the counting is really straightforward. It's just you take the particles, you take the fusion ring with so that's just a ring. You take the ring homomorphisms to the ground field, that's just a set. And that set is in bijection with these equivalence classes. The proof of this, there's a sort of one sentence proof, which is that this is just a statement that this braided 2 category has a non-degenerate S matrix. But well, with David, we gave a kind of purely 2 categorical proof. I mean, the paper with David is really like, we were really careful to do it all without ever using technology, like very motivated by ideas from sort of higher categories and TFT, but never using more than 2 category theory. And so
about your last comment, what is this S matrix? Does it correspond to braiding or linking between?
Yeah, so the way you should visualize it, the motivation, the reason you should believe this counting is that if you have a string, you could imagine taking a sphere of string worldsheet and linking it by a loop of particle line,
Oh, okay.
of particle world
The
line.
rows and the column of the S matrix are on different footings.
That's right. So it's actually sort of the hard part of the theorem. Well, the first step in the theorem was even showing this is a square matrix. It's not obviously a square matrix. And it's like very badly not a square matrix if you take strings up to isomorphism. It only becomes a square matrix if you take strings up to this kind of weaker equivalence relation, this coarser equivalence relation, where you say that two strings are equivalent if you can connect them by an interface. And then, one of our theorems is that in that case, this is a square matrix and in fact a non-degenerate matrix.
I see.
And this is something you should believe is true actually for any four-dimensional topological field theory, not just the ones that you built as a Crane-Yetter construction. I think we will end up with David. We know how to prove that sort of using like the kind of higher category calculus, but for this paper, we proved it really just like using the technology of kind of fusion categories.
Why should I believe this is true generally? Is it related to some remote detectability?
Yeah, that's right. So, well, one reason you should think it's true generally is because Xiaogang said it was 5 years ago. But no, I mean, it turns out that we have a proof that's sort of, it's not completely obvious. I mean, it wasn't something I believed until recently. And it's somehow, the reason it's not obvious is because it's just utterly false if you don't use this coarse equivalence relations. If you really take strings up to isomorphism, it has no chance because you can just count. And it's just, as I said, very badly not a square matrix. What we were able to do with David was to sort of realize, so in fact, in hindsight, the proof is really easy. Like the reason why the S matrix is non-degenerate even in the usual modular tensor category case is because the S matrix realizes the surgery along so it comes from the two torus circle times circle. And it realizes the surgery where you take out a solid two torus and glue it in sort of in a different way. Yes. And the same S matrix also this also comes from a surgery. You can take, like in this case, you can take a two sphere times circle and surger that, so that can be filled either by like a 3-ball times circle, or it can be filled by a 2-sphere times 2-disk. And that surgery is what realizes this non-degenerate S matrix.
I see. Okay.
But that's not, I mean, that's something that we'll write up sometime this summer.
Okay. All right. Thank you.
Theo,
yeah.
I just want to make sure that I understand this comment. So in this example you give about Z2 gauge theory, like this E condensed string would be equivalent to like the trivial string. Would that be correct?
So like in Z2 gauge theory, in general for a G gauge theory, this curly E category is the representations of G. It's the Wilson operators. Maybe I didn't understand the question.
Oh, so I guess my question is that you were giving this example of a Cheshire string where like E charge condensed on this string.
That's right.
And this string would be equivalent to like nothing at all in this definition.
Yes, exactly. That's exactly right. That's an example of a of a string which is not isomorphic to the identity string, but connected to it by this kind of condensation procedure.
I see. And then the isomorphism classes, well, the equivalent classes are just like the usual conjugacy class of G if we are in the G gauge theory.
That's exactly correct. That comes from our theorem, and it's what sort of led us to suspect this theorem. But the special case of G gauge theory in this case was fully calculated by, I'm not going to remember the exact list of authors, maybe Kong, Tian, and Zhang. I know that Liang Kong was on that paper, and I can dig up the reference.
Okay. All right. Thank you.
And Leon's the one I've talked to the most, so that's why he's the name I sort of remembered. But so anyway, this was like a kind of an important part of the calculation. It's sort of a useful fact, I think, actually, even for fusion 1 category theorists. But the main result that we use in our proof is the following theorem, or the first sort of main result, which is that, well, and it shouldn't surprise you. So I took a braided fusion category and built 40 field theory with boundary from it. If I can identify that 40 theory with some other 40 theory, our theorem is that choice selects a non-degenerate category, so selects a 3D, a 2+1D theory, in which these two braided fusion categories live, and they live as each other's commutators. So each one is precisely the anyons which are transparent to the other one. There's a sort of kind of quantum field theory, it's EQFT proof, which is really easy. You just take your 40 theory, or your 3+1D theory. I guess I'm drawing a spatial slice. You take your 3+1D theory, you put its two boundary conditions on it, you zoom out and form a slab. That's now a true 3D theory, and you just calculate the anyons in that 3D theory. Well, and then from this perspective, the thing you have to check, the thing you have to convince yourself is that this 3D theory is still has a local vacuum, has a unique local vacuum. It sort of doesn't have a local ground state degeneracy. And that's a calculation. I mean, but those are all calculations. So that's the sort of fast higher category theory proof. To realize this as math is fine, but you have to use kind of, I think, 5 categories to write this down as a math statement. And well, the calculus of 5 categories is sort of, you might still want to be a little suspicious of any proof that somebody like me tells you that uses 5 categories, because it's probably good, but we might have made a mistake. And so, and so in the paper with David, we actually just carefully prove this theorem, again, always using never more than 2 categories, and using kind of technology from the worlds of fusion 1 categories and rather than kind of fancy picture proofs like this. So this will be my technique for producing non-degenerate extensions. It'll be to realize, I'll inspect, I'll compute the Drinfeld center of this fusion 2 category, and then I'll try to realize it as somebody else. So in particular, this tells me how to solve the minimal modular, the minimal non-degenerate extension problem. So if I can realize the Crane-Yetter theory for B as isomorphic to the Crane-Yetter theory for the Muger center, then I've done the problem. Then I've solved the problem. Then I could sort of take the B boundary condition on one side and the E boundary condition on the other and build this slab. And so the sort of first kind of maybe first punchline is that the minimal non-degenerate extension problem is the problem of classifying 3+1D topological filters. This classification was explained beautifully by Lan Kong and Wen, some of whom I think are here. And Tian talked about it last week in this seminar. So let me remind what they told us. So the starting point of their classification is theorem of Deline's. So the particles in this 3D theory, this 4D theory, in either one, it doesn't matter. They have the same particle content. So that's why you could even believe that they had a chance to be equivalent. Well, the particle content, the anyons, are a symmetric fusion category. And every symmetric fusion category is one of 2 things. It's either the representations of a group. That happens when all of the particles are bosons. Or it's Z2, it's an extension of the representations of a group, which are like those particles which are bosons inside your category. And then there's some super stuff. And so this is the case where your category has emergent fermions. And then we can classify what happens in each of these cases. And let me also say, their work is especially anyway. So I just want to sort of emphasize that if you read their paper, they have some spots where they sort of say, where they kind of have to make some assumptions about non-degenerate fusion 2 categories, but actually the only assumption that they use is this, this non-degenerate S matrix assumption. So their proof applies anytime you know a statement like this. So either this, you know this statement because it's you've proven that it's true for all 3+1D theories, or if you really want to stay purely kind of low categorical, well, you know it's true here, so you don't have to worry about it. So this really is like, although they don't emphasize it, like this really was kind of completely rigorous by now. So let me start with the easier case, just to sort of, and then I'll answer the Meissen's question about kind of Drinfeld's example. So in the case where you're kind of this all boson case, where you're the representation theory of G, what they tell you to do is they tell you take your 4D theory and try to condense, and in fact do condense all of the bosons. And the way you do this, like the reason why you can do this is because you've identified your category as the representations of G. And that's the choice that you need to do this condensation procedure. So you can do the condensation and then you end up with a theory with no particles at all and no strings at all. So it's just the vacuum theory. And you end up with a kind of condensation interface where the bosons condense onto the interface. And then there was this other B boundary kind of on the other side that I used to start with. But I just want you to inspect sort of this part of the picture right now. The condensation procedure produces a G action on this interface. And at the end of the day, what it does is so I mean the condensation procedure is like the whole procedure itself kind of is equivariant for a G action. And so what you end up with is, you know, I sort of started here and condensed to go here, but I could have kind of decondensed. So what you end up with is you end up with the vacuum, but with the vacuum with some G action. So what you end up with is a GSPT on the other side. And so in one direction, I condense all the bosons. To go the other way, I just gauge that GSPT. And so the theorem is that when their theorem says that when the particles are all bosons, so when you're this rep G case, then your full 4D theory is a G gauge theory. And I can really kind of now interpret these pictures so that the condensation interface is the Dirichlet boundary condition for the G gauge theory. This is some sort of like mixed Neumann and matter boundary condition, for instance. So anyway, so as I said, so the punchline is that the original our 4D theory is G gauge theory for some Digraph-Witten action. And on the other hand, if I just used, as a special case, if I just used E itself for the procedure, I would get Digraph-Witten theory with vanishing Digraph-Witten action, sort of the trivial SPT on the other side. And so what you conclude, well, we know where Digraph-Witten actions live. They live in the cohomology of G. I guess I wrote C cross here, but you could do this over any fields, any algebraically closed characteristic zero field. And so this, what you find is that there's an obstruction, in fact, the only obstruction, the obstruction to finding a minimal extension of B is some class in H4 of the group. And that's why the Klein 4 group is the smallest example, because the Klein 4 group has a non-vanishing H4. Whereas like a cyclic group, this always vanishes. And I just wanted to mention that Juven and Xiaogang and Witten give a sort of algorithm that you can use to realize all of these. So you can really go and build you can, if you sort of tell me, if you hand me any finite group, I can go and work a while and hand you back a braided fusion category. If you hand me a finite group and some class in H4, I can hand you back a braided fusion category for which that class is the obstruction. Let me also mention, if you're reading the math literature, that this sort of three-dimensional slab, this 2 + 1D slab, goes under a name in the math literature. It's called the modularization of B. And somehow this total procedure, I've told it to you in terms of 3 + 1D phases, but it was a procedure that the mathematicians had worked out kind of purely algebraically before that, without as much interpretation in topological field theory. So that completely answers the problem of, in this kind of all bosons case. It gives you a complete list of possible obstructions and tells you that they all arise and just tells you what to do. You just go and do this computation. And I mentioned already the Galindo-Venegas-Ramirez paper that kind of, as I said, that does this. And so now I can tell you sort of the more interesting version of the, which is when there are the fermions. This is the hard version of the problem. If there are emergent fermions, so if your particle content is some bosons that look like rep G and then some copy of supervector spaces, again, you can condense all the bosons. And when you condense all the bosons, you're just left with a theory, with some theory that whose only particle is a fermion. And that's how much you sort of know about from first principles. So let's see if we can finish the problem. So I have some 4D theory whose only particle is an emergent fermion. An example of such a 4D theory, so these were studied in a paper of Ryan's from maybe 5 years ago, for example. An example of such a 4D theory is the 4D TQ of T, whose only field is a dynamical spin structure. You could also write it down as a higher form gauge theory. But I recommend you think of it as the theory with a dynamical spin structure, because that kind of connects very much up to the appearance of supervector spaces. If you can identify this kind of 4D theory with the theory of the dynamical spin structure, well, the theory of the dynamical spin structure has a boundary condition, namely you take the Neumann boundary for the spin structure. And now you can compute this whole big kind of sandwich. And what you'll find is that, sorry, I don't want to compute this whole sandwich, but anyway, what you can do is you can kind of study kind of that sandwich, that partial sandwich. And after a few computations, you find that this lets you sort of completely understand this 4D theory, and it lets you solve this minimal modular extension, this minimal non-degenerate extension problem. Specifically, what you discover is that this 4D theory is the theory of, in this special case, let's assume that we understand this, then it is this plus a gauge action. There's some explicit generalized cohomology theory that classifies the possible ways that G can act here, and hence that sort of classifies this our 4D theory. If those cohomological valued things vanish, and if this really is the theory of a dynamical spin structure, then kind of using this Neumann boundary, you can really build a minimal non-degenerate extension. And this is like, if you go through this algorithm, you really do reproduce the Galindo-Venegas-Ramirez kind of obstructions, for example. And I recommend their paper because it's like a nice kind of algebra paper. Okay, so then the question is sort of all boiled down to understanding this theory. So what I just said was I've reduced the problem, this problem of kind of classifying minimal extensions of B. What I've done is I've reduced it to the problem of understanding whether there's a minimal extension of a category that well, in a moment I'm going to start calling it B, but the category that you get by taking this sort of partial slab, by condensing out the bosons in B, by just writing down this category. This is what's called a slightly degenerate category. So that's a category, a braided fusion category whose Muger center is supervector spaces on the nose. And our theorem with David is that those that indeed you do always get the theory of a dynamical spin structure, or rather, indeed, if you hand me a slightly degenerate braided fusion category, it does indeed always have minimal non-degenerate extension. So that was like, that's our big theorem, and I'll say why it's hard in a moment, but let me tell you why it's an easy theorem first. So it's an easy theorem because it has a slogan level proof. So there's a really fun spectral sequence calculation that lets you classify the 3 plus 1D kind of, I'm just writing TQFTs to be a little sloppy. There's a really fun spectral sequence calculation that tells you that the braided fusion category of string excitations in this, given what I told you so far, if must be exactly one of two possibilities. Either it is the theory that arises from a dynamical spin structure, or it's one other possible choice. Except that other choice is a thing which is not a sort of, doesn't look like it deserves to be a valid theory. It looks like a topological 3 plus 1D topological field theory, which has a 4 plus 1D gravitational anomaly. It looks like a theory that has a sort of an anomaly equal to -1 to the W2, W3. And on the other hand, by construction, there was no gravitational anomaly. So this looks like it should complete the proof. So let me tell you why it doesn't. Well, it doesn't complete the proof because for kind of 3 closely related reasons. One is that we just wanted to work algebraically, and it's hard to talk about kind of, or like, do this kind of argument purely algebraically. Another is that braided fusion categories a priori, they don't give you oriented TQFTs. I've been talking about like 4-dimensional TQFTs, but these are the things that you get kind of from abstract principles are not TQFTs, they're framed TQFTs. They're TQFTs that are allowed to couple to a frame. And this supposed anomaly is completely trivial in the framed world. It's only non-trivial in the oriented world. The most damning problem is that the 2 possible framed TQFTs that can arise I actually know how to make both of them non-anomalous as oriented TQFTs. I know how to equip them with orientation data, which does not have a gravitational anomaly. I also know how to equip both of them with orientation data, which does have a gravitational anomaly. So saying like, oh, I go and, well, I for some reason believe it'll have non-anomalous orientation data doesn't help you at all. You might be able to do this by kind of thinking carefully about spin statistics, because the ways that I know how to do this equipment of orientation data, the ones that violate the intuition about anomaly versus non-anomalous situations, they seem to violate the spin statistics theorem, but I don't mean that in a precise sense, because I don't know a spin statistics theorem for string-like excitations. Like, I don't know what it should say. If anybody has like an idea for what spin statistics should say for strings, I think that would be really useful. And again, they also seem to violate unitarity, but I don't know what a unitary 2 category is, so I couldn't use that either.
Theo, can I ask you a question about this?
Yeah.
So I understand that a non-degenerate braided fusion category determines a framed TQFT in 2 plus 1D, but I thought that if I run any braided fusion category through the Crane-Yetter construction, I get an oriented 3 plus 1D TQFT. So what am I missing?
No, I don't believe that has a chance to be correct.
But I thought Crane-Yetter explicitly construct a state sum given any braided fusion category. And that state sum is topological, like it's truly topological, not just framed topological. That's what I thought Crane-Yetter.
So unless I'm very mistaken, so if I start with a unitary braided fusion category, for example, then it's certainly, you get an oriented state sum model in 4D.
So it's unitary. Okay, so it's
and actually even that. So what you get from kind of abstract nonsense is that just a braided fusion category gives you a framed Crane-Yetter model. Ribbon braided fusion category, like a pre-modular braided fusion category, gives you what's called a combing on that Crane-Yetter model, meaning that it lets you put it on 4 manifolds with a line field. So you can rotate sort of in 3 dimensions. And that 3 dimensions are the 3 dimensions parallel to the boundary. And that's because like the braided fusion category is living on the boundary. And then if you choose a 6th root of something, like a 6th root of the quantum dimension, like there's never an obstruction to extending that combing to a true oriented field theory, but the choices are a choice of 6th root of some number. That's what I thought the status was.
Maybe it's the adjectives that I have confused, because I thought that like a unitary braided fusion category is the same as an example of a spherical fusion 2 category, and then I can use
That's exactly right.
And then I can use Douglas-Reutter to construct the oriented 4D TQFT.
Absolutely, that's absolutely correct.
So it's the unitary. It's the unitary thing that
the unitarity is doing a lot of work for you there.
Okay, so it's dropping unitarity that then you go to this world of framed versus oriented that you have to work.
Yeah.
Okay.
And I should say, like, David and I did kind of explain a proof of our theorem back in November that had sort of much closer to the argument I tried to give that used unitarity. And kind of, although we don't know what a unitary 2 category is and we don't know what spin statistics should mean for 2 categories, we have some intuitions that it should like be something that includes a bunch of properties or implies a bunch of properties, and then we could independently kind of show that we had those properties. But yeah, if you're not unitary, or if you don't give yourself a ribbon structure, then I don't think that there's any hope. And if you give yourself like a non-unitary ribbon structure, say if you're non-unitarizable, there's perfectly good braided fusion categories which are just not unitarizable at all. In fact, actually, work of Reutter and separately Galindo, like if you combine some results of Reutter and Galindo, being unitary really is a property of a braided fusion category over the complex numbers, in the sense that if you're unitarizable, you're uniquely unitarizable. But there's plenty of non-unitary. Like, first of all, you might be unitarizable, but you might decide to choose a non-unitary ribbon structure. Like you might just kind of decide to violate spin statistics for the hell of it. And also it might be possible. You might be looking at the Yang Li category.
What's your formulation of spin statistics?
I don't have one in for strings. That was what I was saying.
Well, would it be enough to say that like a fermionic string, if you want to create it locally, you need to have a W3 structure? Because that's how I would think about the spin statistics theorem.
So an example of the spin statistics theorem is that so what spin statistics in general tells you is it tells you that some property of an object called its statistics matches or provides some property of the object called its spin. And so an example of this is that if you have an abelian fermion, well, that's an abelian particle whose braiding with itself is -1, minus the identity. And those particles always have the property that if you also go and rotate them 360 degrees, that action is minus the identity.
But there's like a picture proof of this, right? Which is something just topological that I think also works for like framed spheres, not just framed curves.
It's perfectly reasonable to build models, like whether you have, so statistics is something purely about the framed field theory and about the kind of like, it's purely something you can measure without ever rotating your framing in spacetime. Spin is something which by definition has to do with how your field theory is equipped with an orientation structure. Unitarity should tell you that there's a unique, like the philosophically, there's a unique unitary way to equip a spin sort of orientation structure on a bosonic theory. But there's non-unitary ways to do it, which explicitly violate spin statistics. And so what you should do is you should think of spin statistics as being a property that may or may not hold of an oriented quantum field theory. Or in the case of braided fusion categories, it's a property that may or may not hold of a ribbon braided fusion category. So Juven has his hand raised.
Yes, I think a question about spin statistics. So I think let me phrase some physical way. And I think this type of spin statistics statement, mathematician might call topological spin statistics, like what in paper they also write this topological spin statistics. But in physics phrase, I think the spin here just means the self statistics. And perhaps that's just the framing you're referring to, the self statistics in the sense of for point particle will be 2-pi rotations, while the statistics here will be exchange statistics. So there should be some relation between self statistics and exchange statistics. That's the picture.
Okay, that's right. I mean, that's I bicker a little bit with the words because anyway, I totally agree with you that yes, what I mean is that like something about a single particle being rotated is identified with something about two identical particles being switched.
Yeah, so that's a relation between self statistic and exchange statistic. But then my question for you is that because you say something is not known for the strings, but in physics,
well, maybe it's known. I just don't know it. I mean, I don't know what the full statement should be.
I don't know either. I certainly I don't for math proof, but for physics literature, we do a lot of dimension reductions of strings by compactifying. It's more like a decategorification, going one lower. So changing the string excitations by putting it in one compact circles and reduce that to a low dimensional excitations.
Yeah.
By in the compact direction, you can trace additional flux. So it's more like reducing some data, for example, modular SL3Z to decompose to modular SL2Z. In that sense, a lot of topological spin statistics for the strings relates to topological spin statistics of dimensional reduced particles, but insert with some background. Generally, in a group theory sense, label will be some conjugated class of fluxes. Okay. But I don't know whether this is enough to give you something the topological spin generated strings that you need. There are some stories there. Yeah.
Right. So I don't think what I have in mind and what we needed to sort of what seemed to be true about like these wrong orientation data that I have in mind is that they were quite subtle, and really you had to look at the flux world. Like there's a sort of flux string in both of the two theories that's magnetic, the sort of magnetic string state dual to the electron, and any flux loop, if you kind of close that flux string into a loop, it just becomes the vacuum. So you're not going to get very much progress just by looking at just that loop of that flux loop. You really need to do something a little bit more local on the flux string world sheet. So I think all I want to say is I think there's sort of a lot of open questions. I mean, I think it would be an interesting thing for people in this audience to think seriously about. It's like, what should the kind of complete statement of spin statistics be for higher dimensional objects in general? And
thank you. Thanks. I'll send you some reference anyway. Thank you.
That would be really helpful because my guess is that there are things people have figured out that I'm not aware of. So. Anyway, we wanted to sort of avoid that. So let me tell you a little bit more about these theories so that I can actually tell you what our algebraic proof of our theorem is. So I'm going to use some facts that came from, I told you that there was a spectral sequence calculation. So my input to the problem is that I have a braided fusion 2 category, which is sort of, I'm looking at this sort of, I start with a slightly degenerate braided fusion 1 category. I then ask for the 2 categories string excitations in its Kramer-Yetter model. What I know about that category, because we carefully proved it in sort of in 2 categorical, in terms never using beyond fusion 2 categories. What I know about that 2 category are 2 things. I know it's a braided fusion 2 category. That's like thing 0. Thing 1 is that its only particle, its only non-trivial particle is some emergent fermion, which I'm going to call E for electron. And I know that it has exactly one kind of equivalence class of strings, which is I'm going to call M, which is the for the sort of magnetic string, this flux string, dual to the particle. And their relationship is that that if you take the electron and sort of, this is like a 4-dimensional picture. So this is a picture of take the electron and move it around the M string back to where it starts. Yeah, in 3 + 1D. And the relation is that action is -1. So you input these things into a calculation, and then a spectral sequence later, you conclude that there's exactly 2 options. And I want to sort of quote a fact that kind of comes out of that calculation, which is the following. So you can take this M string. It turns out, and this was a non-trivial fact, but it turns out that this M string squares to the vacuum. And it turns out that, in fact, it generates a Z2 one-form symmetry on the whole thing. Like there's no, so that there's some implicit thing in this statement, which is that the M string, if you kind of take the M string and cross it with itself, that's the isomorphic to the identity. So you can look at this Z2 one-form symmetry. Z2 one-form symmetries in 4 dimensions are classified by the 5th cohomology of Z2 of the Eilenberg-MacLane space of Z2 in degree 2. With again, I wrote C cross, but I should have written K cross here. I mean, you could do this over any field. Doesn't matter. So the anomaly of the symmetry is definitely classified by that group. That group's a Z2. So the anomaly is either trivial or it is this specific non-trivial anomaly, which is has a name. It's called -1 of the SQ2 SQ1. And the calculation is that for the thing we want, for the kind of theory with a dynamical spin structure, this Z2 symmetry really is not anomalous. It's just a true, good, gaugeable symmetry. And for the other one, the one I want to rule out, it has an anomaly. And so that's what I'm going to use, rather than talking about gravitational anomalies, which I don't have access to, because that has to do with like orientations. I've moved the problem to a measurement about a 't Hooft anomalies for symmetries. Like about kind of the obstructions to gauge, so symmetry anomalies. So that's why I can do this really framed and never have to have any kind of unitarizability. So I'm kind of almost done with my proof. I think I have 2 or 3 slides left. So I'd win if I can decide what the anomaly of this Z2 one-form symmetry is. Specifically, I would win if I can find an anomaly indicator, for this anomaly, and if I can calculate it. It's no good to have an indicator that you don't know how to calculate. So I'll just tell you the answer. I mean, we worked for a year to come up with this. And then in hindsight, it's really like, in hindsight, we know sort of just those stories that would have told you how to find this, but we just had to work and work. So I'll just tell you the answer. So here it is. Here's a picture. This is a picture of a Klein bottle. Let me unpack this for you a bit. So here's a picture of a flux loop of M string framed as a figure 8. So this is the non-bounding spin structure on this flux loop. And something I can do is I can take this loop of string and I can just rotate it in space as a figure 8. And I do a 180-degree rotation, and it comes back as another figure 8, but oriented in the other direction. So loop those two around. So now I have, so I can, what I'm doing along here is this is the mapping cylinder of 180-degree rotation of this flux loop. And importantly, the point I want to make is that that 180-degree rotation changes that 100-degree rotation in space changes the orientation of this figure 8 flux loop. On the other hand, I know that my magnetic string is self-dual. I know that it squares to the vacuum, which means I know that I do have kind of defects that I can place along the flux loop world, the flux world sheet, which reverses the orientation of the world sheet. And so just insert that defect along a figure. This is a sort of somewhere along the cylinder and wrap it into a torus. So the total thing here, this is the mapping torus of the composition of reverse the orientation using your knowledge that M is self-dual, and then reverse the orientation again by 360-degree rotation. And when you draw this out, when you draw this mapping torus in 3+1D, you get a Klein bottle embedded in 3+1D. Specifically, you get the Klein bottle with non-bounding pin plus structure. And in fact, you don't even need a pin plus structure for what I'm going to do. It's like a sort of more like a pin C structure is what I'm using. So this will be my anomaly indicator. This is the thing I'm going to measure to determine my anomaly. And then you could just trust me. It's like another kind of cohomological calculation that this indeed does calculate this is indeed an anomaly, an indicator. It does indeed measure the anomaly of Z2 one-form symmetry. The nice thing about this particular indicator is it doesn't require that the input be a Z2 one-form symmetry. You can make sense of this Klein bottle as soon as you have any object, any string in your system, which is self-dual. You don't need it to square to the identity. You only need it to be isomorphic to its dual. And then you can do this construction and measure this. But in the case where it is isomorphic, where it is sort of does square to the identity, where it's an invertible object, then this does measure the anomaly of that Z2 symmetry. Okay, so this is what I'm going to measure. And now I need to use one last trick. So remember, what do I want? I have some specific 2 category of strings that I care about. I know it has some specific invertible object in it that generates a Z2 one-form symmetry whose anomaly I want to measure. It's actually really hard if you write this down kind of in a Crane-Yetter style. If you write this down in any method you want, if you'd like actually start with a braided fusion category and actually write down this 2 category, you get a 2 category, which is equivalent to one of the two categories I told you, but that equivalence is complicated. And it's actually quite hard to explicitly identify this simple magnetic object. So there was a question, but I think it should be for later. It's actually really hard to identify this explicit magnetic object, this sort of simple magnetic object, if you model this in terms of a braided fusion category, like if you sort of start with a braided fusion category and try to do the calculation. It's hard to identify a specific simple magnetic object, but it's easy to build a non-simple magnetic object, a magnetic string which is a superposition of a bunch of strings, some composite state. Let me tell you what this composite magnetic object is. So there's going to be 2 steps to it. So the first step is, by construction, my 4D theory has a 3-dimensional boundary condition. So this is a spatial slice. Wrap that around a cylinder, and wrap it around with boundary framing. So Blackboard framing. This gives you a canonical string. So this, remember, this is a spatial slice that I'm drawing right now. So this is really a picture of a string in my two category. It's really this is really a string. And then this picture is really terrible. So this is a string. It's this is a string world sheet in 2+1D, in 3+1D. Any string in my category has a local operator on it called loop the string with an electron. So it's the local operator that kind of creates a pair of electrons, runs one of them around, and then it annihilates the pair of electrons. That's a local operator on any string. Like that's I don't know. Ryan tells me I'm supposed to call these instantons. That's an instanton on any string world sheet in this system, in particular in this one. And it's an operator that squares to the identity, which means that I can look at the projector 1 plus or minus that operator divided by 2. So what you should think of is that what I've drawn now is like, it's like I loop the string, I bead this, I put a little loop around my string by a particle, which is this virtual particle. This virtual particle doesn't exist, but the corresponding operator does. And it's an idempotent. And so I can then, like that idempotent projects me into two different eigenspaces for that idempotent, the kind of plus and these are like the eigenspaces for this loop of electron. And so I get these two, I get that what I find out is that like there's this canonical direct sum decomposition for any string in my category into these two pieces. And both of these are still composite. They both have lots of summers. But I have one guy who's kind of purely magnetically charged. Okay, well, and now I'll finish the proof for you. So I have this guy that I just built that I really know explicitly. I can really write down a very explicit description of it in terms of my original braided fusion category. I know it is purely a kind of magnetically charged object with a sum of magnetically charged simple strings. So it's a sum of these m's. Just for a moment, just imagine taking any orientation reversing isomorphism of this object. Well, all of that isomorphism, this is a sum of m's. This is also a sum of m's. M is self-dual. Now, your choice of isomorphism might involve some permutation of those. That's okay. So pick one. In fact, I know this object so explicitly that I have a favored isomorphism here, which just has some permutation of these. So it's some permutation. Now I can calculate this kind of Klein-Bottle invariant for this magnetic object. Well, the Klein-Bottle invariant, as I told you, the Klein-Bottle is a mapping torus, so it's the trace of an operator. What operator? Well, it's a trace of, there's a -1 if I'm in the anomalous category. In general, it's like whatever the sort of invariant just of a simple magnetic string is of the flux loop. And then there's whatever this permutation matrix is. And I don't know very much about permutation matrices, but I do know that the trace of a permutation matrix is always non-negative. So the trace of minus a permutation matrix is always non-positive. So I do know that this invariant, if I'm in the bad case, if I want to rule out the bad, if I'm in the case I want to rule out, then I would end up with a non-positive value of the invariant. On the other hand, a different calculation lets me just calculate this directly. And it really uses that, as I said, we have very explicit control over this object. Like I know exactly what you get when you wrap it around this figure 8. And the calculation shows that this is some sum over particles in my original category of some formula. Well, it shouldn't surprise you. It was something like 1 plus or minus e times something, but the second term just is 0 and the first term is positive. And so that completes the proof. This invariant is positive strictly, which means that it cannot, which is not non-positive, which rules out that case, which means that my original 4D theory really was the dynamical spin structure I wanted. So thank you for your attention.
Thank you. Well, we have time for some questions. Could you tell us the just so story about the anomaly indicator?
Sure. So I can tell you let me tell you like iteratively. So our invention of it was kind of terrible. So we were trying to really figure out an algebraic way to calculate the gravitational anomaly for this 4D theory. And this 4D theory, like I start with a 4D theory, which I tell you as a non-degenerate braided fusion 2 category. So what do I mean by its gravitational anomaly? Well, I literally mean like the corresponding invertible 5D theory, which has some explicit model, its value on non-bounding oriented 5 manifolds. Namely, its value on the Wu manifolds or on any manifold coordinate to the Wu manifolds. An example of a manifold coordinate to the Wu manifold is I can take CP2. Complex conjugation on CP2 is orientation preserving. So you can take the mapping torus, a complex conjugation of CP2. This is a thing homologous, coordinate to the Wu manifolds. So I would want to evaluate my invariant there. Well, because it was a mapping torus, the value of the 5D invertible theory is the trace of an operator on this Hilbert space of this CP2. The Hilbert space of CP2 is given by a scheme theory for my braided monoidal 5 or my braided 2 category. And so then we started actually working out what that scheme theory was. That's how we actually invented this Klein bottle, was doing that horrible thing. Then once we had it, we realized there were much better descriptions. We wrote it down, recognized it was a Klein bottle, and then started studying it. So so one thing that I can say is the following. So what am I trying to do? So I'm trying to distinguish two things. I'm staring at KZ2, and I'm trying to distinguish the map SQ2, SQ1 to KZ25 to H5, Z2. Let's call it what it is. Yeah, just write it what I had it. That's the thing I'm going to try to distinguish, is this cohomology class. And so my strategy is going to be, let me map into it. Let me try mapping into it from some Tom spectra or some sort of Bordism spectra, MTG. So let me try mapping in from, sorry, what am I trying to say? Let's just work with stable objects. This is a stable class. So let me think of this as a map rather from HC2 to HC2, that's a degree 5 class, a degree 3 class, HC2 and degree 3. So let's just try to do it. Let's just, rather than trying to invent the problem I really want to do, let's just try to do the stable version, the kind of commutative version of the problem. So I can try mapping in from various MTGs for various Gs. So actually, sorry, what I really mean by this is the following. So let me try to say it even better. So even better, what I really mean is I can take what I really want to do is I want to take the cone. Yeah, sorry. So there's a spectrum which looks like kind of HC2 in degree 3 into degree 2. mapping to HZ2 with Postnikov class SQ2, SQ1. This is the spectrum I want to be able to sort of distinguish. So this the homotopy groups of this are Z2 and Z2, and everything else is 0. So there's this precisely 2 spectra with these homotopy groups. There's this one, and there's just the product. So what I'll try to do is I'll try to map in. I'll try to take sort of various cobordism spectra and pick a map from the cobordism spectrum to HZ2, and I'll try to lift those maps. Well, this is just a map from. This is the data of the downstairs map. Is a map from. This is just a map from pi0 of MTG to Z2. This is whatever it is, and then I can like look at. So let's say I lift it, and then I can evaluate. F on pi2 MTG. That's going to be my strategy for detecting the spectrum. And this is somehow the same as like, if I can do this, MTG is the cobordism spectrum for manifolds. So if I can do this, it will suggest to me a kind of an anomaly indicator that's sort of like the one I told you, that's about kind of wrapping surfaces on manifolds. So you could try various groups here, and so for instance, like if you put, MTO just doesn't work. The non-trivial map on pi0 for MTO just doesn't lift. MT spin just doesn't even see it. This map becomes trivial. But if you're clever, what you realize is that actually kind of MT pin, that the spectrum X really is the 2 truncation of MT pin plus. And pi2 of MT pin plus is generated by the Klein bottle. So that's a reason why you invent the Klein bottle. There's actually an even better reason to invent the Klein bottle. I'm going to assume that somebody's going to tell me if I should look at the chat or if it's actually just like people talking, which is better because there should be lots of that. There's actually an even better reason to look at the Klein bottle, which is that there's some unpublished work of Douglas, Schomer, Priest, and Snyder that they've like talked about a bit, but they haven't finished the paper, so I don't want to like use it too well. They have some work about a really small cell model of the kind of homotopy 3 type of BSO or something like that. BSO3, I should say. And if you take their skeleton of BSO3, you can use it to build a really small model of KZ22 by attaching a Klein bottle on, and then just see that this is really that invariant. But like some of those results are results that I hope that they put in their paper, because we sure don't want to write them down carefully. Ryan, did that answer the question?
Yeah, I mean, I was kind of surprised by the approach. I guess like I was thinking of something like, I don't know, like some kind of Smith homomorphism that you reduce to 2 dimensions and then see that you have to have pin plus. It's kind of a cool trick with to use the anomaly as the Postnikov class.
Yeah. I mean, as I said, this wasn't what we did the first time. Like the first thing we did was tried to figure out what the scheme theory assigned to CP2 and how complex conjugation acted on that.
Mm-hmm.
And then at the end of the day, we just sort of saw that our invariant was a Klein bottle, and then tried to reverse engineer a story that would make the Klein bottle obvious. And well,
I
I
see.
mean, if you know cobordism spectra inside and out, you might know that the Klein bottle generates empty pin plus in degree 2.
Yeah, I have a comment. There may be another way to look at this indicator, but I'm not sure whether they are equivalent or not. So this anomaly indicator can be viewed from this point, from another point of view. That is, this string have this worksheet, space-time worksheet. Okay.
Yeah.
If you assume a string worksheet is non-orientable, and then there will be a line of orientation, reversal line. That's a word line.
That's exactly right. Yeah.
And then this word line must be a fermion. So this is another, maybe saying the same thing. Maybe that's another way to say this anomaly indicator. I wonder whether this is consistent with what you say or not. We just have a different way to understand this. But this with the word line is a fermion loop, then depend on other details, whether fermion get a 2 pi twist or not, maybe minus sign or no minus sign. There's a those are I don't know. Yeah, but roughly speaking, there's an argument. Say this orientation reversal line must be a fermion word line.
So I don't know how to interpret what you just said, Shogun, because this is a line confined to the world sheet.
Yeah, it is
the
a
world
line.
sheet's only 1 + 1D, and so the line confined to the world sheet doesn't have a spin. It doesn't have statistics. So it doesn't make sense to ask, is this a boson or a fermion? Now, something you could do is you could take a fermion off the world sheet and bring it to the world sheet. But actually, if you take the orientation reversal line and bring a fermion from outside, bring my sort of electron rather from outside to which is like my kind of fermion particle, and bring it to the world sheet, I just get another orientation reversing defect. And I didn't emphasize this, but something that's really cool is that actually it doesn't matter which orientation reversing defect you use. So there's 2 different orientation reversing defects that differ by a copy of the ambient electron.
Yeah.
And they both work, and they both work for the calculation. They give the same Klein bottle invariant.
I see.
But yeah, I mean, there is something along the way that you're saying, which is explaining why.
I think we need to think a bit more carefully. But basically, what you just say, the fermion word line has to bound on this orientation reversal line. It's something along that direction. And but I think we need to think more carefully about how to, these words may not mean anything. I totally agree with you. It's better this indicator better to be a number at the end.
Yes.
Right now we still have tried to see whether.
Well, I mean, the indicator I drew really is surface in 4-dimensional in 3 + 1D. I didn't emphasize it, but in order to I mean, so this is a surface, so it does resolve to a number. Like this resolves to a number.
Yeah.
And it turns out to be either +1 or -1.
Yeah.
Now there is something that I cheated you, which I didn't cheat you very much. I in fact didn't cheat you. I just didn't emphasize it. So this surface is topologically a Klein bottle, but not every Klein bottle works. Like I emphasized already that the pin plus structure is non-bounding for this Klein bottle.
I see.
But actually, to tell you surface like this, it's not good enough to tell you a Klein bottle with non-bounding pin structure. I have to actually give you more tangential frame. I have to give you more tangential data than that. I actually have to locally frame the surface. And I have to make the framings, so the orientation reversal gets to switch one of the 2 directions of orientation and keep the other one parallel.
Yeah.
And I have to also, so I have to frame the surface, and I also have to I have to frame the normal bundle to the surface.
Okay.
And it's not obvious the way I drew it that the normal bundle is framed. In fact, I did not draw this with normal. Yeah, I did not draw this Klein bottle. The blackboard, the sort of four-dimensional blackboard on this Klein bottle does not tell you how to normally frame the surface. You have to use a different normal framing. But
okay.
So there is some sort of other work you have to do.
To convert the picture to a number, you may need additional data like a framing, normal bundle,
That's right.
normal difference, things like that.
That's
Okay, thank you.
And it does all work, but the actual definition is take the composition of rotate the figure 8 180 degrees, composed with do this orientation reversal defect. That's an endomorphism of this figure 8 of this kind of. And now take that endomorphism and trace it, and take the trace you get to do. So in your symmetric fusion category of particles.
Yeah. Thank you.
It's a little bit surprising because actually this, if you just look at this, this is actually sort of something really I just want to mention too. Like if you just looked at a little strip of cylinder of this, the flux string, if you kind of loop it around the flux loop, that's actually the vacuum particle.
Okay. Yeah.
So the fact that this can resolve to -1 is already something slightly weird. But it can. I mean, -1 is a perfectly good trace of an endomorphism. It's the trace of the endomorphism called -1.
Sorry.
Thank you.
What particle do you say? Axion? Sorry. What particle?
Sorry?
What do you say about the particle? Axion? I just misheard something. I'm not sure what I misheard.
This four-dimensional theory, this 3+1D theory, has precisely two isomorphism classes of simple particle. There's the vacuum particle, and there's the electrically charged particle. So this, if you take the magnetic string and put it in a little loop, it will become either the vacuum or the electron. Turns out it becomes the vacuum. It's sort of not a very hard calculation.
Do you mean like shrinking this loop will give you a?
What I really mean is that this flux loop has a way of ending. So that there is a way to fill in, although I used the non-bounding framing to give the flux loop. Although if I had closed it up with blackboard framing as just a circle, then it would obviously end because you could just like take kind of the cap. But because I use non-bounding framing, it doesn't obviously end. Rather, it non-obviously can end. Kind of as a cross cap or something.
So by ending, you mean like you fill in a disk in that sense?
That's right. That's right. There's a way of filling in this this loop with a disk, even though the spin structure doesn't match.
I see.
So a related question about this is that I suppose you probably wrote about it in another paper, but this type of invariant can be defined for 4+1D TQFT, is that right? And it's always just plus and -1 for a self-dual string type object?
So maybe
maybe I misinterpret. I don't know, but I think the word Klein bottle appear in one of your papers, so the other paper of yours.
Okay. Yeah. So right. So I know what you're talking about. So yes. So here, if you work really hard, so the Klein bottle does embed in 4D. Like not every surface embeds in 4D, but the Klein bottle embeds in 4D. And it embeds in a way which can be given all of this framing data that it needs. And so that means that this Klein bottle invariant only requires the data of a braided fusion 2 category. Like if you can evaluate it for any self-dual object in any braided fusion 2 category. Now, you might have had more ambient dimensions than you needed. Like it doesn't have to be, your braided fusion 2 category doesn't have to be this one. You could do this for any braided fusion 2 category. I mean, for any 2 category with duals. For any braided 2 category with duals, you can evaluate, and a self-dual object, you can evaluate this Klein bottle invariant. Now, you might have more than a braiding. You might have a soleptic or symmetric 2 category. And that would correspond to working in more than 4 total dimensions. This is this doesn't cost you. I mean, if you actually care about a situation in 7 dimensions or in 5 dimensions or whatever, take the Klein bottle I drew for you. It lives in 4D. And now just embed 4D into 7D in the standard way. Now you have a Klein bottle in 7 dimensions that you can evaluate somebody on. It turns out that, well, and then there's some facts, which is that I told you what the anomaly of this, I told you this class, but I actually cheated you. I wrote down a stable class, not just a class. I mean, I didn't cheat you. I gave you more information about this class. So this is a class that this is actually a stable cohomology operation, which means that it is a sort of meaningful and important thing in any dimension. And yeah, so this invariant sort of stays, this anomaly indicator stays an interesting anomaly indicator for like
But you're referring to
-1 form symmetries and whatever it is. There's like this was a 1 form symmetry in
always
3
an
plus
anomaly.
1D. But there's that in any large dimension, if you have a symmetry, if you have a Z2 symmetry who's like generated by a string. So what P form symmetry that is depends on your ambient dimension. But if you have a Z2 P form symmetry where P is whatever from the ambient dimension, the anomaly will always be, there's only one possible non-trivial anomaly. It's always this one. And this Klein bottle always evaluates it.
Oh, so any non-anomalous theory, I'm supposed to get 1 doing this Klein bottle stuff. That's
yeah. This is sort of a side effect of our work. Is like I can tell you how to calculate anomalies of Z2 P form symmetries for some specific value of P.
Got it. I see. I see. Thank you. Yeah.
Should I, Ryan, are you chairing or should I just call in people?
Yeah, go ahead. Call on whoever you like.
Okay, I think I saw Hank's hand go up first.
Yeah. Hello, Theo.
How are you?
I'm good. I'm good. I have 2 questions. One of them is quite naive, I guess. Like, can I interpret the this problem of the existence of a non-degenerate extension of your braided fusion category as a form of seeking a non-anomalous bulk? Like the
yes.
slender is equivalent to the trivial theory.
That's right. So that's exactly right. So I think the picture I want you to keep in mind is that like I drew it sort of here. Where did I draw it? I drew some picture. Here we go. So we start with some braided fusion category. It selects its bulk theory. And now what I want to do is I sort of want to trivialize that bulk theory. I want to recognize it as an untwisted digraph-Witten theory, or sort of an untwisted, an untwisted gauge theory. And it's exactly that recognition, sort of that like trivializing the bulk in a certain sense, that is what gives you a boundary condition, which gives you a. So this bulk theory could have lots of possible boundaries you could put on the other side.
Right. Yeah.
For most of them, the boundaries you can put on the other side, they come in they come in various classes. So first of all, the boundary on the other side might or might not have confined string states which are non-trivial. If it has confined string states which are non-trivial, which like don't end as on the boundary, and you build this slab, what you tend to do is that'll affect that then you won't have an embedding. So you'll get a map from B to M, but it won't be an embedding. It'll just be more like a quotient map. So if you want this to be an embedding, you need this guy to have basically only particles and the kind of Cheshire strings that they produce.
I see.
And then the next thing that could happen is that this guy might have lots of particles. And that's fine. That just means that your embedding won't be minimal. So what I really want is I want this to have only particles and to have as few particles as possible.
Okay. Now the question is, like, we can go conversely, right? Starting with a bulk that maybe there's a way to characterize the anomalies in the bulk as you just did with the Klein bottle.
Yeah.
Like, if we can compute for a given bulk theory, if we can compute that anomaly, then we can say that it emits a anomaly-free boundary condition, this B.
That's right. I mean, that's basically what's going on in kind of in general. That's what's going on in all of this in kind of all of this obstruction theory.
Okay.
It's like for any bulk theory, for instance, if your bulk theory only has bosons, then we just know what the bulk theory is. If the gauge theory where boundary conditions for this are exactly theories with a G-symmetry of anomaly that you can compute from this bulk.
And then we can build like a lattice model on this.
That's
boundary.
exactly right. That's
okay.
right.
Yeah, that's great. That's sort of like a unifying picture from, because I've read condensed matter literature where they have they characterize fractional quantum Hall systems with these filling indices, the invariants, and there's a certain combinatorial equation that they satisfy, which looks very much like an anomaly-free condition. So in that sense, there's a way to characterize, I guess, fractional quantum Hall systems as boundaries of these anomaly-free boundaries of these bulk theories. Also, the second question is that I've seen Klein bottles show up in, for example, in crystalline SPT phases, where the space group is the glide group, PG.
Yeah.
Yeah.
Yeah, I think you're telling me about this.
Yeah, that's right. So I was wondering, like, what is it like in that scenario? What does it do to the anomaly? I
have no way to comment on that. I think,
okay.
Like Ryan and Dominic are both here. They should chime in if they want.
Yeah.
Sorry.
No, it's okay. Thank you.
Can you ask it again? Sorry.
Yeah, so I was just wondering, because the classifying space for PG is the Klein bottle. And there's this Klein bottle construction where Theo just loops this string around. I can think about looping a string around the tube, I guess, of the Klein bottle, and then using the glide operation to basically have the same picture, essentially.
Yeah. I mean, I think if I understand correctly, maybe Hank's asking, like, if I care about, say, roughly two-dimensional field crystalline lattice models that with glide symmetry, then kind of a fundamental domain would be a Klein bottle. And maybe the question is sort of, is that related to this Klein bottle? More importantly, like, are there, more importantly, kind of, can our anomaly be useful for that? But I don't know. Can our anomaly indicate? Somebody else should ask you a question. Ryan, you need to like call on people. I don't want to do it.
Let me.
Okay, I'll call on Juven.
So question is naive. I think you motivate even more in the end about this Klein bottle construction, and you put the symmetry defects on this Klein bottle. I think you say this is a 3+1D with some non-bonding pin plot structure. And my question is that because we know Klein bottle is a connect sum of two of the real projective RP2 space.
Yes.
I wonder whether there are some similar statement you can also make on RP2 instead on Klein bottle. Just for my interest on RP2 for some other reason, I just wonder whether there are similar statement for the RP2. Thanks.
It's a great question. It's not one that I've thought carefully about. My gut reaction is no, for the following reason. In general, to wrap a string around a manifold, around a surface, to wrap a string state around a surface, You have to equip that surface. In general, you either have to equip the surface with tangential, with like framing type data, or you have to equip your string state with extra data which tells you how to rotate, how to not have to use framing data on the surface. And in any case, I don't believe that RP2 can be equipped with enough framing data to do it for what we wanted to do. I do believe that our magnetic flux could be equipped with enough sort of orientation data to be wrapped on an RP2, but it would have made our calculations much harder to like try to, because we would have had to work out what those data were. And so that's why we didn't.
All right, thank you. Thanks.
I think next is Meng.
Yeah, I actually have a question about this slide exactly. So the picture that you drew here is this slab construction.
Yeah.
And let's say we take this example of Drinfield's example where some braided fusion category is not, you cannot find minimal modular extension.
That's right.
And the bulk is actually a twisted D2 gauge theory. But I can still put this B on one side of boundary, and the other side have this condensation interface.
Yes.
Where condense all the charges of this D2 gauge series. Yeah. What goes wrong with this construction? Is that
great question?
Not correct, or?
Great question. So this is something I should have maybe, yes. So from the gauge, let me just start by saying that from the gauge theory perspective, that if I think of this as if I recognize this as a gauge theory, then the condensation interface is the Dirichlet boundary. And what I want to do is I want to put the Neumann boundary on the other side to build the minimal modular extension, the minimal non-degenerate extension. If I do look at this particular slab, it does give me a non-degenerate category, but it's not an extension of B, it's actually a quotient of B. It's like you take B and quotient out the anions. So that's sort of the Muger center.
Semyon theory to start with.
Yeah.
Okay, so this condensation is not a condensation of charge. It's a condensation of flux in some sense. Or maybe that's not very precise language.
Well, and I come I only know what I read in papers and try to learn language sort of through osmosis. So my understanding of the way that Lan, Kong, and Wen want you to think of this is that this is the boundary condition on which the particles here condense. So particles can end if the boundary condition itself has confined string states. But no particles, no confined particles. If you take any particle here and move it to the boundary, it just becomes the trivial particle in the boundary. But this
is not the boundary you like, or
no.
Okay.
So what the way you should interpret this in terms of gauge theory is that this whole slab gives you a quotient of B, which in mathematics is called the modularization of B.
Right.
This you should think of as pure Dirichlet boundary. B itself is you should think of as a mixed as like a kind of, so if you want to think of B itself, so there's some gauge fields in the bulk. They have Dirichlet boundary on the red side, and on the green side, what you have is you have matter fields from the modularization together with Neumann boundary for the gauge fields, and those are coupled by the way that G acts on the modularization. So this is like a Neumann coupled to matter boundary. Now it's a general thing that if you take sort of Neumann and Dirichlet, they cancel out. And that's why you get back the modularization.
Right.
And what I actually want to do is I want to take Neumann with Neumann, because if you take Neumann boundary, that's the same as gauging one dimension lower.
Right, right.
And that's what that's what my goal, that's what I'm after.
So what you want is a Neumann boundary without any matter. And then
that's exactly right. That's exactly right. And to choose Neumann boundary, that's right. So what I want is to put Neumann boundary with no matter on this side. And to choose a Neumann boundary with no matter is exactly to trivialize the digraph-Whitney theory in the book.
That's right. Yeah. Okay, yeah, that just clears my confusion. Thank you.
Next we have Sahan.
Hi. So I have a question. So for lines, we have this notion of a Frobenius shore indicator that you can compute it whether you have braiding or not, meaning in 1+1 or 2+1. And so my question is this indicator that you define, could you also define it in 2+1 for any surface? That meaning that if you only have a fusion 2 category?
Great question. No, because it was a Klein bottle. And if you wanted to be able to do it in just a fusion 2 category without braiding, then the things you get to compute without a braiding are things you can embed in 3 total dimensions. Like the general calculus here is that you have like the dimensions parallel to the string world sheet is your sort of category dimensions. So I'm in a 2 category, so I have two directions parallel to the world sheet. And then you have as many orthogonal dimensions as you have kind of monoidality. So monoidal just means you have 1 transverse direction. Braided monoidal means you have 2. So 4 ambient dimensions, 2 + 2 is the best possible because that's what you can embed a Klein bottle into.
Okay, I see. Thank you.
I mean, I guess there's a chance that there's some magic in like fusion categories are better than arbitrary monoidal categories. Fusion 2 categories are better than arbitrary monoidal 2 categories. There's like things that you don't have the right to do from kind of abstract scheme theory that you can do in the fusion case because of semi-simplicity. So there is a chance, but I know it won't work. Okay, here's why I know it won't work. I know it won't work because these 2 braided fusion 2 categories that I'm using are isomorphic as monoidal 2 categories. And the only difference is they're braided. So there's no way that this invariant will be measured just from the monoidal structure.
I see. Yeah, because in one category, fusion 1 category, there are 2 formula for the Frobenius shore indicator, and one is just uses that. But you're saying that I see, that doesn't work. And is it so for fusion category, you could like define like the end Frobenius shore indicator also? But I mean, is there a way that this can be defined? Certainly not with a Klein bottle, but
it's not something I know about. You know, fusion 2 categories are brand new. I think there's just a lot of open questions. Like, I think you should go and do it. Like, I somehow think that everybody should start working on fusion 2 categories and should sort of figure out what we can and can't do there. There's like a lot of ways that they're the same, that they're similar to fusion 1 categories. There's some ways that they're different. There's a lot of questions, so I don't know.
I see. Thanks.
I have one more question about the Klein bottle invariant.
Yeah.
So can you comment on like how this is possibly, I mean, it must be related, but no, how is it related to this notion of fermionic string that Ryan introduced in his paper that's related to like trivialization of a W3 structure?
Ryan, can you remind me what a fermionic string is for you? I've read Ryan's paper a couple of times, but I don't remember exactly. It's not in front of me.
Well, it's very similar to like a fermionic particle where like if the world sheet is a sphere with a certain framing, then you get a -1 factor. So it's to like the linking number of the push off from the sphere with itself.
I mean, a priori, I'd have to, I'm not.
But I don't know what it has to do with the Klein bottle, because the Klein bottle is for, well, yeah, to have a non-orientable world sheet, you need to be able to, it needs to be like a Z2 object.
Right, or at least you need to be able to choose an isomorphism between your string and your and its orientation reversal.
Mhm.
Yeah,
It's somehow related to this anomaly.
yeah, so
What-
one of the things that can happen is that, like, of course, if you take a string, just in general, if you take sort of two copies of the same string, you can just forget about the direction of the string. You could just like take a slice one dimension lower and just ask what happens when you cross them. So I'll even draw a picture because I think I can draw this. So you can ask what happens like if you take kind of a string and take another copy of it and kind of, here's a picture where it moves behind the other one. So this is like just a standard crossing times 0, 1. And so this is going to be like the braiding of the string with itself. And for this could be, it might be like if the string is invertible anyway, then this will be isomorphic to the identity times some particle, like going along kind of some line, and you can ask like, what particle is it? You know, and what your allowed choices are depends on what your particle content is. I'm in a setting where the particle content has this like distinguished particle called an electron, which kind of behaves as if it's -1 for certain properties. And so it could have happened that this particle could have been -1. It turns out that it's just the vacuum. In my case, but it didn't have to be. That's a very naive notion of what it means to be magnetic or to be fermionic.
Mhm.
And from this, I think you find, so Ryan told me he wanted me to take, well, I don't know how to take two sphere. Well, okay, so I mean, I could take a sphere and push it up, a two sphere and push it off itself. And in 4 dimensions, and like those will braid, if I try to force them into 3 dimensions, they intersect along a circle.
Right.
So Ryan said, let's take a 2 sphere and let's push it off itself. So those are intersecting along a circle.
I thought you
where
actually
one of
want to
them
push
goes
outward.
below the other.
I think you actually want to
Oh.
push outward, so that when you rewrite it in terms of like a kind of like rotating a particle, instead it's like rotating the string about its core.
Oh, I see. So you're really asking about what I would call spin. You're really measuring something that's about the action of rotation.
Yeah. That's why I called
Okay.
them. Yeah, they're fermionic, like in the spin sense. I think there's also a braiding. You can also say that they braid fermionically. So there is like a spin statistics.
Which I see that Juven also sent a bunch of references. So that's not something like, I think there's something, I'm sure there's a lot to do there, and I don't know it. I'm hesitant because, as I tried to say, like, if I just give you a string excitation, it's extra data that I'd have to tell you how that the string world sheet can be rotated. And there might be a kind of canonical choice of that data or a best choice of that data, but it is extra data. And that's not data that I know how to parameterize or compute with very well.
But for instance, in this theory that has the W2, W3 anomaly, it's sort of crucial that not only do you have a fermionic particle, but like the string that braids with it is also fermionic in this sense.
Right, the string that braids with it is the one that I'm calling M. Yeah, so I found a different way to see that crucial difference that didn't use that fact.
Okay, so what for you? What was it?
For me, it was that you take, so this I'm always using red for the string that braids non-trivially with the fermionic particle. So here it is.
Oh, okay, sure.
This is something that never requires that I actually, like, when you look carefully at this Klein bottle, you can give it both a tangential framing and a normal framing, so that that you never have to be able to rotate.
This is for the one form anomaly, right?
But so the way I told it to you is this is a thing that measures the anomaly of the one form symmetry generated by this string.
It's the same, right? This stable operations S2, S1 is the same as cut product with a W3, right?
That's exactly right. That's why that's basically why it is this.
Well, I was talking about a pure gravitational anomaly.
Well, that relies on the W2 part as well, but you can just look at W3 cut product with a Poincare dual of the string.
Yeah, but what does that have to do with W2, W3?
W3 is SQ2, SQ1.
Yeah, I know. So it's like W3B, but that's not W3,
but
W2.
B is this string is this string is the string which is like lives along a surface Poincare dual to W2.
I just mean that if you put a C2 gauge theory on the boundary of W2, W3, and you can write W3B and W2 of the one form A. That's what Ryan you
No,
wrote.
there's two different anomalies. They don't have to be the same thing.
I totally agree with you. They don't have to be the same thing.
Yeah, but
they turn out to be, well, or rather, it turns out.
Yeah, if you said B
only
equals
theories.
W2, then you get the gravitational anomaly. It's true.
I think just
and I would have loved to be able to use the purely gravitational anomaly, but I can't because I don't have access there. I don't have good algebraic control over orientation data.
Okay, now I understand why you had this one form symmetry.
So I had to do the measurement in terms of the one form symmetry instead.
But the Klein bottle applies to the more general one, I guess.
Yeah, but you're right that the reason why it works is because like somehow I'm measuring either kind of, basically I'm measuring like kind of SQ2, SQ1, or whatever it is of W2. That's right. I'm measuring, at the end of the day, like I'm measuring SQ2, SQ1, W2. Well, SQ1, W2 is W3, and SQ2 in dimension 5 is coupling with W2. So.
Yeah. Also, for this Klein bottle invariant, I mean, it doesn't seem like that the definition only involves a string, right? So how do I see that this invariant just doesn't exist at all for, say, a 3+1 Z2 gauge theory with a bosonic charge, not even an anomalous one?
You have to calculate it.
Well, you can define the indicator, no?
Yeah, I mean, this anomaly indicator is something that makes sense, as you said. In fact, it doesn't even require that you're a true Z2 one form symmetry. It's something you can define as soon as you have a string together with a chosen isomorphism. This is data that you have to input. You have to choose an isomorphism between your string and its dual. And if you change that isomorphism, it may or may not change the value of the invariant.
Right.
You have to compute it. But it's a thing that you can compute in any braided monoidal 2 category together with an object in this choice.
Okay.
And you could go and compute it for Z2 gauge theory.
Yeah, just wondering why you get these two series.
Yeah, and for
in the fermionic case, but in bosonic case, you just get one. It seems.
Right. Yeah. So for Z2 gauge theory, for Z2 gauge theory, it's more subtle than the way I told it to. So for pure Z2 gauge theory in 3+1b, I've been talking as if there's only one magnetic string. But there's actually two different magnetic strings that can have a non-trivial interface between them. And there's no a priori reason that this invariant is going to be the same for both of them. Just like there's no a priori reason that the invariant doesn't depend on the chosen isomorphism, and it might depend on this isomorphism. And I think in the case of Z2 gauge theory, yes, in fact, I know this is true. In the case of Z2 gauge theory, one of the magnetic strings, this evaluates to +1, and the other magnetic string it evaluates to -1. And the choice of isomorphism is irrelevant for both.
Okay, so sorry. So you mean that in a series with emergent fermion, you also get these two types of magnetic strings, but they evaluate the same Klein-Bode invariant.
That's correct.
And
that was an important calculation we did in the paper.
And these two magnetic strings, do they differ by?
They differ by stacking with the Cheshire string,
or something like this.
They differ by stacking with the Cheshire string. Like there's an interface between them,
okay,
which looks like cliff 1. So it's like,
okay,
they're kind of, it's like their ratio is cliff 1 in a certain sense.
So basically, you stack on this magnetic string 1+1 invertible fermionic TQFT.
That's exactly right. That's exactly right. They differ by the 1+1D theory, which is like you want to think of this whole ambient 4D theory as if it has a dynamical spin structure. And so it has sort of like a 1+1D theory, which is like the Arth invariant for that dynamical spin structure.
Okay.
And that's the ratio of the two magnetic strings.
I see. That makes a lot of sense.
I mean, it doesn't quite make sense to me because it was a dynamical spin structure, but that's the way that we should think of it.
Yeah.
Maybe that's correct, and Ryan will just know that it's correct.
Okay, all right, thanks.